So first of all, I want to thank you all for attending our talk today, and also Databricks for the opportunity to present our work. So I'm very excited to share our experience building out data lakehouse and onboarding data pipelines to the system for the past few years to power a lot of components of our business, especially ads. So for this session, I would go over the challenges we have managing the complex and very large-scale ETL pipelines when the business and data grows exponentially during and post-pandemic. I will also talk about the solutions we adapted in the past 2 years to build out a better data platform for scale and productivity. So then we will cover or do deep dive on some use cases related to the events ingestion. And then lastly, we will go over the transition from supporting batch-only data pipelines to also supporting streaming and incremental processings on Lakehouse. So before we go into the subject, I would like to introduce about Instacart and ourselves. So Instacart is a leading online grocery platform. We are available to more than 85% of the total household in the United States, and more than 90% of the total household in Canada. To achieve this, we're partnering with over 700 national and regional, also some local retailers, including special brand names only available in specific areas. We also offer self-serve and managed ad service by partnering with over 4,000 CPG brands to ensure their campaigns and products can reach to our end customer on the platform. So about me, my name is Arthur Lee. I work on the data platform team at Instacart, focusing on the batch processing infrastructure, including compute, storage, and monitoring. Here's my colleague, Devlina. She's on the ads measurement team. So their team is focused on building out the data system and attributions for the retailers and CPG partners to see the ROI on our platform. So before we get started, I want to just share some numbers or facts about our data. So we have over 1,000 internal frequent data users. So these users includes engineers, data scientists, and machine learning engineers who really need the data to build the system to power the Instacart business. We also have users who are executives or leadership who just want to understand the overall health of our business and see where's the growth opportunity using the data we collect and processed. So combining the data lake and the data warehouse we have in the company, we have over 40 petabytes worth of data. So as a marketplace company, you can see we have a lot of data and a complex use case, which pushes us to really build a scalable and a cost-effective data platform to power different needs. So one specific areas we use data to power is ads business. So next, I will pass on to Devlina to talk more about ads management and data use cases.
So Instacart has a wide array of ads product. If you have Instacart at any point of time, you might have come across our sponsored products, display or video ads covering the full ads funnel. And we provide rich set of tool chain to our customers, which are advertisers, to create, manage, and track their performance, ads performance. These ads metrics are critical for our business and as well as to maintain our advertiser trust. They not only track their ads and campaigns live through these metrics, they can also tune their ads based on how the ads are performing. So just to get a glimpse of how the pipelines look, This is the general flow of most of our ads measurement pipeline, where stream of data from different platform and different devices are collected to by our event streaming platform, and the payloads are stored in warehouse for further processing. Ad measurement platform comes within that rectangular box. It takes the data, which is the raw blobs from events, and then passes through several business transformation and mutations, and prepared a structured format for data and stored it in data warehouse, which is further processed or consumed by online serving or machine learning and further other business analytics use cases. Today, most of our topic is covered around how different problems we faced in that step 2, and how we address them through Databricks solutions. Just to consolidate all our problems, they are mostly categorized into these 4 groups. When we started building ads measurement platform about 3-4 years ago, our goal was mostly limited to, we had a product and we had to build few pipelines for that. Serving those metrics quickly and which can be shared across the teams and can be consumed and directly can power the production dashboard was our main goals. But as our business grew, the number of product line increases, number of pipelines increases, the complexity of that business logic which those pipeline processes has now becoming more complex and complex day by day. We have reached a point where cost is a concern. Like, we have to bring sustainable solution to maintain our growth over next coming years, as well as we have to do things more efficiently as we move forward. One aspect of this area is our code itself. As you can imagine, those pipelines were simple SQL pipelines which were easy to write. Anybody can write a single file script quickly, and we run those scripts on shared warehouses, which were right choice of tool back then. But as the team grew, the next point is showing that the pain point in collaboration and sharing those code has increased. And last but not the least, testing is very important for ads measurement pipeline, just because of the nature. We power the budget and bidding optimization by ad server. So accuracy of those metrics are our topmost priority. So our testing has to be up to that standard, which with current or existing tooling, we were limited in terms of our testing by just running those production SQL code, mostly on a test warehouse, nothing more than that. With that, I would pass to Arthur to take you through platform changes.
Thanks, Alina. So with the limitation we're kind of facing, it was clear that the SQL-only based data warehouse system we use cannot be scalable or cost-effective for all our use case. So we start to really look at what are requirements we want to have for our data systems. So after discussing with different product and engineering teams, it really comes down to these 3 areas. So we want to have flexibility on different type of language support and low-cost storage for our data in object storage, and also interoperability with different type of compute system, including Spark, Trino, and also different training frameworks such as TensorFlow and Ray. So for the multi-language support, I guess what we really want for different group is for the core data infra team, we want them to build out the Scala applications so they can adapt software engineering best practice and also maximize the performance for the application they built. And for ML and data scientists, we want them to be able to access the data while using their favorite tools in Python. And most importantly, so we want the system to be still able to power the regular or most common use case, which are pipelines we already written in SQL. So besides the multi-language support, I want to talk a little bit more about the using object storage. In this case, we're using S3 to store our data. It's because, as I mentioned in the previous slides, we have a large amount of data. We have over 40 petabytes size of the data, and most of the historical data we have stored in the storage. We don't really frequently access them, but we pay an equal amount of money if we store those data in a proprietary data warehouse or storage solution. And also we have tons of new data being ingested every day to power different components of the business, including customers, shoppers, and also ads. So with S3, we can just leverage the intelligent tiering or manual lifecycle policy to really save the cost for our historical data. But at the same time, we can also retrieve those data if there's a need on the compliance or audit purposes. So for the features or cost requirements we have discovered during this phase, we decide to really just embrace this concept of Lakehouse. So what the benefit we're really looking for with Lakehouse is just the unified data platform. We can process the structured and unstructured data in the single storage with a different type of compute we can just plug in, including Spark. And also we can power different type of use case, not only just batch use case, we can also do incremental processing, just process the data once it's become available in our Lakehouse. And also, as I keep emphasizing, we want to have a cost-effective storage because we just have so much data. And more than that, we want to be also run advanced analytics workloads. So not only just SQL, we want to power different type of workloads using the data we store in the Lakehouse. But there are some challenges with Lakehouse with the benefits it provided. For example, with S3, the permission management usually tie with the IAM roles. So we really need to develop a good solution for the engineering teams to manage the permission and data access to ensure they're not just log into the AWS console and just configure the permission they need. And also for the data application development support, this one is a bit interesting because before we only have SQL workloads. Now we have those applications, so we need to provide corresponding development workflow and also CI/CD support and monitoring for people to deploy and develop their applications. So for the permission management side, what we did is we developed a self-served permission management module based on Terraform. So this provides an abstraction for engineering teams to manage permissions for their own data at S3 prefix level. So engineering teams will use this module, basically making change on the permission change, and just submit the PR to the platform team, and we review the PR and approve it. After the PR is approved, CI will trigger the corresponding policy change associated with the PR, then apply to our IAM roles and account belong to the engineering team. And also for the CI/CD and pipeline development workflow, we basically just have the users develop and test their code on the local laptop. And once they finish the development, they will push the code to GitHub for review and create a PR. And after the PR is reviewed and approved, the engineer will merge the PR, then the CD service will be triggered to run the test again and package the application with all the dependencies and deliver that to the Artifactory where it can be picked up by the computer resource. So in this case, we use S3 to store all our artifacts or application jar code. So with all the support we kind of built or developed for the data applications, so next step is for us to really bring in the data, to ingest the data to our Lakehouse. So this is the diagram of our previous events ingestion system. So essentially, with we have a variety of different data source, but in this case, we have mobile client and the internal services that sending data to the event ingester, and from there, we actually leverage a managed service provided by AWS called Kinesis to ingest the data and use Firehose, which is the service provided by Kinesis to deliver the data to S3. So there were several limitations and problem with this architecture, which make the data we have on S3 really hard for the end user to directly use that. First, Kinesis at the time doesn't really support table format, such as Delta or Iceberg. So that means for end user, it's really hard for them to know when the data is going to become available for them to actually process, or after they restart the application, they don't really know where they left over when the application was shut down. And second, Kinesis also doesn't support dynamic partitioning based on the event payload or value. I think recently Kinesis added that support, but it's at an actual cost. So you need to pay actual money to have your data kind of partitioned on S3 according to the events payload. Also, on top of that, Kinesis is already very expensive. But Kinesis, it's a managed service. It's expensive for a reason. Basically, it saved all the engineering time needed for the resource training, all monitoring. It just provides you a service, and you hook up with your data source. Then you can start writing data to S3. But it's just too expensive for us to actually use based on our event volume. So what we did is we actually replaced the Kinesis stream and the firehose with Kafka and Spark structured streaming. So what it does is once the ingester receives the data, instead of sending to Kinesis, it will just forward the data to Kafka topics. The Kafka topic is basically just become a source of truth for all our streaming data source. And after that, we'll have a structured streaming application consuming from that Kafka topics and write the data to S3 incrementally. So for the data we landed in S3, in this case, we actually use Delta Lake to store all our data, which provide a built-in fault tolerance and also ACID transaction support, the versioning, and also schema enforcement. We also partition the data according to the events type and date time. So we basically just further divided the data into smaller chunks. So during the data scan or data retrieval, when user file the query against this data, they can only scan the data they needed for the query if they have the filter on the partition specified, compared to previously, they have to grab all the data and figure out how to filter out those data when the data is already being retrieved on the compute node. So with this new architecture, not only we're able to deliver the data in a timely manner, but we're also able to achieve this at a fraction of a cost compared to the previous system. So with the data source become available in the Lakehouse, next I will pass on to Devlina to talk about how we actually build data pipelines on top of this.
So just to have to visit it again, that the data pipeline is basically consuming the data from those warehouses earlier, which in earlier Arthur's slide, Arthur presented that they have replaced it with the Delta Lake. And we now replace this system with a streaming application, which can directly use those Delta Lake as a streaming source. So before going into that, I would give you a little bit glance of how our pipeline used to look before. We did have incremental pipeline in with warehouses as well. These are batch pipelines, and we used to have the custom windows to manage those sliding windows. And this is just two cases of example cases where how we manage those custom windows. Ideally, the new window should start or process only the new incoming events, but due to always like out of order events and late arriving events, we err on the side of reprocessing instead of missing metrics and thus producing inaccurate computation. Along with those custom windows, we have several modes of processing. The schedule mode is basically the regular mode, which is the pipeline is auto-triggered at a periodic interval and then process the data frame it is left off at the last time. The manual trigger mode is basically used to fix or reprocess the data, basically used in backfilling or any data fixing process. And then the time to manage those windows, we have several types of time we were using. One is based on event time. We also have ETL time based windows for handling different edge cases. So we replace this incremental model with which actually is a very good fit for streaming use case. But before going with Spark structure streaming, but before going into Spark structure streaming, I just give a primer of how Spark has what kind of streaming support Spark has for those who haven't used Spark streaming before. Spark actually provides two kinds of streaming. Their first version of streaming was abstracted as dstream API, which is mostly different streaming API construct, which underneath uses RDDs to perform those streaming applications. And then it basically treats the input data stream as batch of data, and then it breaks it down into multiple batches and then operates on those batches internally. Spark structure streaming change or simplify this a lot. So now they have the streaming works on basically for a user, it works on a static table which behaves like an infinite batch pipeline. So as a user, I can still use my data frame and data set operations. So I don't need to rewrite my pipeline which has already been working as a batch pipeline. I can use the same transformation logic with a little difference in the way I can read and write the data, and that's it. Then I don't need to repeat those logic again, or which simplified our migration a lot. And with that structure streaming, we replaced that top section, which was our earlier version, with the section below, where we are using delta table as our stream sources. And this event deserializer is shared between batch and streaming. So we saved a lot of time in migration. Basically, generally the streaming API requires a lot of learning, and to rewrite again our all event deserialization would have taken time. But with structure streaming, we just reused our transformation, which was implemented using data frame APIs. And our batch job is basically used during backfill and reprocessing, and stream job is our regular mode. And with that, we also simplified our various modes and consolidated them into just two modes. One is the backfill, which is to correct or reprocess data, and regular mode is streaming. And there's just a slight difference in the way we are reading the data in these two modes, and which is highlighted in that code. And you can see that the only difference is that just one API call, and the rest of the options are almost similar. Same thing is with write. In stream mode, which is our regular flow, we just call stream APIs to write the data at S3 locations, which is again, we apply the delta metadata on top, which are basically delta tables. From delta tables, we also store them in different warehouses for analytical use cases, but in machine learning and for the data pipeline, they use delta tables directly. For check window processing, which was basically earlier custom implementation, is now we are using Spark constructs to handle our windows. So no more manual or custom code for window handling. Everything handled out of the box through these checkpoints. We store the checkpoint location, checkpoint in S3, and Spark works based on those version given in the checkpoint, and it starts the processing exactly where it's from the last version where it stopped. So that was our incremental pipeline or micro batch story. But with that, I will come back again on the first points where I showed that how there are 4 pain points with our existing pipelines. One was the cost, and the other was how our codes has been written. So when we used SQL to write those pipelines, it was the right tool to select for a small company, but as our pipeline has grown in complexity, the most time we face that there are a lot of shared code across those new product lines, and there is no building blocks actually for us to use. The way we used those code is basically copying and then creating a new pipeline by copying those codes. And you can imagine that how bug fixing and making a small change and chasing around all the code where it has been copied is so hard to as the code base grows. And of course, no modularity and composability was there. And there was no real unit test actually. So all the test was basically limited to you copy the SQL and run in some test warehouses. And those SQL has to run end to end. There is, yeah, of course you can go and slice and dice, but then it is a manual operation and developer has to take their time to, if they want to just cut like a slice of the code and test that part. So it was pretty heavy lifting work. With Spark, since we now got, we wrote most of this pipeline in Scala, and with the general purpose programming language, we addressed these problems from the ground up. We constructed most of our ETL in these building blocks, and these are the entry points how most of our pipelines are written, and they are exactly what they say, that there are 3 steps for each pipeline: extract, transform, and load. And extract and load step are basically shared code which all pipelines can share. And any data source or databases can be, new connector can be written. And for example, right now we have Snowflake, we have Databricks connection, and any new data source can also be written as a connector, and our extract and load will be able to handle that. The transform is nothing but composition of various business logic. And transform, again, earlier it was just a big chunk of SQL file. Now it can be broken down into these logical units, just like any regular programming language. So now data pipeline development also feels like regular software engineering and not just writing SQL scripts. So these are just few example methods which a transform might be doing, and these methods then can be shared across different pipelines, and they are properly unit tested as well, local. And the advantage of unit test here is basically we are doing all this in-memory test with a pretty small data stub. There is no network cost involved. So as long as developer is still in experimental mode or they are writing new logic, all their tests they can do in memory with small data set without incurring any extra overhead or network cost. And once they are ready doing developing their new logic, they can move that code for further testing. But here we are getting huge productivity improvement, because we are getting like this feedback loop for the developer as they are writing code and testing is now much faster. Earlier, we used to write a script, then run it in a shared warehouse, and based on the load of the warehouse, the time also varies. And then we were running really large queries on large data, which used to take a lot of time. So with SBT tooling, SBT is that Scala build tool. We have now this like regular general purpose tooling available at our disposal, which we can use to write and iterate fast. One thing which we got out of the box from Databricks was basically schema. So even though we are moved to Lakehouse architecture, which is basically supports the unstructured data, our requirements for data pipelines were actually enforcing strict schema. So we were still using structured data, but using all data constructs. So one thing which we had to build to migrate the system is strong schema enforcement. Though Delta, even it is a Lakehouse architecture, it provides schema on write constructs, which is required to enforce the schema on structured data set, and we just directly use it out of the box. And Delta has this nice blogs, actually, if you are interested to read more about how they are doing this. So we saved a lot of time by, for us not to write a new system for handling the schema, and which was like a pretty big win there. So once the developer is done with local development. Due to this nice feature Databricks have, which is like job cluster, we can run those code with production-like data on shadow environment, like these are test environment, but with a more realistic data set. And earlier, we used in our data warehouse, shared data warehouse world, we used a time-shared staging environment for any real cluster testing. So what happens then if it is already in use, the developer has to wait until it is free next time. We reduced those times, and actually there is no wait time now, ideally speaking, because two developers, they can work on the same pipeline, they can change the same piece of code, but they can run those code totally independently on those shadow clusters. The word shadow here just means that they are not production data, they are using production-like data but not mutating any production data. And since Databricks provides the control over instance sizes, we are also using those features to control how, our resource sizes based on our requirements, which again helps us to control our cost of those resource uses, which earlier was not possible because we had to tune, those levers were available at warehouse level, which was pretty difficult to tune it for each and individual jobs. We got a lot of win on monitoring side as well. Earlier, our monitoring was limited to job level, like whenever we had Datadog integration with our data warehouses, though we were pushing those metrics on basically as a job completion status. So job failed or passed, we got those kind of metrics. And then for any data quality checks, we were basically using SQL-like queries on our production table to see if, to detect any anomalies on that data. It was okay, but again, having monitors on production table means that anything which could go wrong has already gone wrong, and now we are just reactively checking the data and fixing it. With Scala, we now are able to instrument the intermediate stages of our pipeline. So most of our pipelines work as a state machine, right? Like, which is a collection of few states where one state depends on the output of previous state. And with this monitoring and intermediate stage instrumentation possibility, we can now check the output of those intermediate states and fail fast. So if we detect any anomaly in our intermediate data set, we can stop the pipeline there and take appropriate action without doing a lot of wasted processing to go till the end and then fail. And also with Scala, we got this test coverage tooling to measure our testing coverage, which was not possible earlier. With that, those are mostly our win I wanted to share today, but we are not stopping there. With these advanced tools, now we have the possibilities ahead of us, which the team is already working unit test frameworks. By unit test framework, we already have now a unit test, like where people are locally testing by stubbing data, but we can improve it more by seeding data automatically. Like what developer wants that with a few button clicks, they want to seed prod tables, and so for their local testing as well. So the team is working on those kind of features. We have advanced monitoring capabilities which we are working, like Datadog traces and APM logs, generalized pipeline framework. So most of our pipelines share a lot of common building blocks, and so we are developing a framework to abstract away all the boilerplate, so developers can directly go and write the business logic without thinking about the setup of their environment for each pipeline. And we are improving our schema management to work it cross services. And that's all. And Arthur and I are representing the work of a big group here over many months of collaboration between Instacart and Databricks. So thanks all of the folks to bring us to this state. And with that, I open for questions.